To begin to understand blood flow, we need to know about the different types of energy found in the body. The energy gradient is the difference in fluid energy found in a vessel. This difference is the reason blood flows. The energy gradient equation shows us a little bit more about fluid flows through a tube. The energy at the beginning of the vessel must be different from the energy at the end of the vessel. And then the side with less energy is the direction that blood will flow into. If the energy at the beginning of the vessel equals the energy at the end of the vessel, then no blood flow can occur. There must be a difference in energies for blood to move. One of the reasons that blood moves through the body is due to pressure energy. Pressure energy is created by the heartbeat and is in the form of potential energy. We can define potential energy then as energy that is static or stored and can be converted to another form of energy to do work. Let's look at a few examples to help illustrate potential energy. So one would be a coiled spring, one that's pushed all the way down before it releases. Another example would be a bow and arrow, where the bow is pulled back, or even the arm of a quarterback right before they're about to throw a ball. The potential energy is found right before some sort of work or movement. Another pressure energy that is found in the body is called hydrostatic pressure. We'll be covering more of this in detail later. But for now, you need to know that hydrostatic pressure is the result of gravity on a tube of liquid, or for our purposes, the circulation system. So that hydrostatic pressure is the result of gravity, which creates gravitational energy. Gravitational energy is yet another type of potential energy, and that any object that is elevated above the Earth's surface has the potential to do work. To illustrate this concept some more, let's take a look at another few examples. For example, we have a skier sitting at the top of the hill. Gravity has not yet moved them. They are in a position where they can potentially do work. Another example would be a rock sitting at the edge of a cliff. If that rock were to fall, that rock would be in movement doing work. Right now, it is storing potential energy as it sits above the Earth's ground. A last example would be a ball thrown in the air and frozen right at the apex of the throw. So pressure energy and gravitational energy are both types of potential energy. That potential energy is something sitting still with the ability to do work. Once that work is converted into another energy and begins movement or begins that work, we call that kinetic energy. So stored energy turns into kinetic energy to put an object in motion or to start work. Think back to the examples that we use for pressure and gravitational energy, the types of potential energy. That potential energy transforms into kinetic energy when things are in motion. The spring is sprung, the arrow is released, ball thrown, the skier starts to move down the hill, the rock falls, and the ball returns to the hand. If potential energy is still, then kinetic energy is moving. Not all of the potential energy is transformed directly into kinetic energy, though. When blood is flowing through vessels, there is some energy loss. Potential energy is mostly transferred into kinetic energy, but we'll also see it transferred into viscous energy loss, inertial energy loss, and frictional energy loss. A liquid's viscosity indicates how thick or sticky something is. Viscosity is the fluid's resistance to flow. Blood made of red blood cells, platelets, and other objects is relatively sticky. A lot of energy is used to move blood to overcome its own thickness. Think about making breakfast in the morning. If you pour syrup on your pancakes, you can really squeeze the bottle, hold it upside down, and the syrup is just going to slowly pour out. Pouring a cup of juice, though, you barely tip that bottle and the juice easily comes out. The syrup is more viscous and requires more energy to get moving. Inertia is the name given to the principle that objects tend to like to do what they're already doing. So a ball rolling down the hill will keep rolling down the hill until some sort of outside force or energy changes that path. Blood flowing through vessels would much rather just keep going down the same tube, but we know blood has to take different avenues to deliver oxygen and nutrients to our whole body. When blood takes a turn through a vessel, it converts some energy into slowing down and making that detour, and this deduction is inertial loss. Think about driving your car. It's much easier to stay on the highway. You'd get everywhere you want to go much faster, but eventually you do have to get off the highway, so you have to slow down and take that exit ramp. As blood moves through the vessels, the very edge of the blood comes in contact with the wall of the vessel. This contact point, albeit minuscule, causes friction. That friction then causes some of the kinetic energy to be lost to heat energy. We see something similar in the winter when we're really cold. We rub our hands together and they start to feel warmer because of that transfer of energy to heat. The last concept that I want to introduce, now that you've learned about all the different energies in the vascular system, is the idea of conservation. Energy cannot be created or destroyed. It can only be converted. So let's say the potential energy that starts in the left ventricle will be converted into kinetic energy and to heat. That kinetic energy and the frictional energy, when added together, must equal what the potential energy was. No energy is lost or destroyed. It can only take on different forms. So I'm curious how many of you thought of this slide when I said that all the pressures must be equal. What the energy gradient really wants is for a difference in subtypes of energies. A lot of these energies are going to be found in multiple ways in the vessels. But what it really wants is a difference between kinetic energy on either side of the vessel, or a difference in pressure energy on either side of the vessel. Without it, the flow would not occur.